Hey, while you're whistling, while you're working, you got a center mass mastering tonight. You got a mastering a moment of mission EK Rising Monday night that you hopefully started on. I've added in some reading here, 12.6 and 12.10. You hadn't checked out the previous reading for today. We're going to do some more moments about moment of inertia today. I don't think we're going to get to angular momentum. We'll save that for Monday. And then, like, the week's all screwy because I asked keys. There'll be a test probably at some point towards the end of next week. But we're going to see how that goes. And then there's one more unit after that before we start review. So that's kind of where we are and where we're headed. I have this right. You have the tension. You're working out what right now? Moment of inertia of the cylinder, like the thing as a whole. Okay, cool.
What is this equation that they're using?
So we have a linear motion equation, Fu ma, and so there's an analog for rotational stuff that says that the unbalanced torque equals the rotational equivalent of mass, which is the moment of inertia, times the rotational equivalent of acceleration, which is angular acceleration. Yeah, so that's probably what they're doing. All right, so things that we know.
The unbalanced torque? Okay.
Yarp.
This was like that's the
Yeah, so what is the reading?
What do you need to know?
Can you explain to me what was going on?
Were you not here yesterday? Oh, okay. Yeah, that's good to know. Yeah, so pop over this way. And on your way by Thomas, can you grab those two cylinders? And whoever's here is going to need to move
It gave us what was the yeah. Yeah.
Oh, no, just doing this.
Is there anybody that was not here yesterday and needs the explanation of what the heck we're doing? Hop over this way.
Jake, where'd Oxygen?
He's
Where's Dr. Schultz?
Not what you can definitely use.
So you signed tonight?
Does it mean the?
Yeah.
I'm doing it right now. You got the right
Yesterday we had so starting. This is useful.
Wow, I wouldn't even raise
Hey.
Oh, okay. I equals the integral or
And so they use Is this a here or is that meant to accelerate down? And now You're saying
I'm looking
that's
at all of
yes,
these
that has to be four lines being applied of spindle. Radius
I was like,
force spinning applied to humanization. Look at this. Like, this is gonna make this rotate. Here's the axis.
Oh,
It's a very huge change. So
oh.
the new equation that we introduced yesterday is that a bounce part equals one angular acceleration. And it operates just like that. Yeah. Angular tied together.
Inertia equals the sum of the masses times the radius squared. The radius is
Meters per
equal to
second.
inertia equals 117.
so instead
I don't think so.
of using one half
Max, no, 0.117.
Yeah, yeah. The meters is
No, it's just like.
Why does he have so?
You guys had this.
Hi, Eric. I don't know, probably took me.
Yeah. How did you already get a math?
Figured it out? Yeah. Okay, do you wanna kind of explain this? Okay, so. So that's the thing, yeah, the diagram, okay. And then we did,
What do
these
you have?
are all our known variables. Diameter, diameter
Oh, you
what?
guys started.
The spindle. Of the, okay. And then times 14, 7 seconds.
So you have to.
Do we know how many times that went around?
well, during the calculation.
Okay, and so then, using math, we did this, because we need the mass, or, okay, we did this, because the tension, the gravity, minus, because we're looking at tension is the gravity minus, sorry, can you help me with this? What? Okay, so the pulling that way is equal to gravity minus the pulling. Gravity minus the pulling of just like
You guys
the
found
energy.
the mass yet?
Alright, so just a
The
slight.
mass or the
And
energy?
then, like,
No,
yeah.
the.
What, so you
Oh, funny. I know these are 6, 6, and the other one said 5 times, but I think it's supposed
I'm not understanding.
It's the rope back.
So the tension
So the other thing
is like, okay, so gravity of the tension in the rope, like this, right? Yeah. Okay. This is your gravity, is that what you're talking about? Yes. This is your tension. This is your absolute. So it's just like if you, I understood this yesterday, okay. No, you're fine. Gravity, tension is what we're finding that makes it.
it's really if you actually keep playing.
Okay,
You're not. No. I mean, I was
so
like
when you're
shocked.
trying to find FU,
If you watch it,
yeah.
go to the.
You guys divide that out?
Yeah.
So what is this? This is tension, gravity is like, I think that it's just like additional objects because
Like, we got like.
that's like kind of what's pulling it because it's going down.
Okay.
No, but it's taking more energy to spin it rather than pulling it down. Because you know, like that, as it goes down, it takes energy to spin.
Oh, hey.
Relatively speaking, simple.
Why would you consider that? Oh, okay, okay.
So I think we can do
I don't think it is
So
not
like,
gonna make.
it's kind of like accelerating, you know, slow down,
so
or slow down.
hard.
These are the things going faster. As it goes faster, like there's gonna be some acceleration as it pulls down. And this is like, if there was no,
Small spindle.
you just feel like a
What we have.
I just don't know what that equation is doing.
It's saying like how much like
Wait, why does it get worse?
maybe rotational.
What's this do?
It's just like,
What gives you?
it's just like the sum of all the forces, or like how to, so there's three forces out here, it's like the gravity and the tension, okay, and then just like the force that it takes to move it,
Rotational?
kind of, but like, that just torque, the inertia.
Yeah, because like they're getting attention.
Like, I believe that you guys understand that, I just want to. Mr. Hardy,
What up?
they're trying to explain to me FT equals FT minus FU, and I don't understand.
Because if you
Drew a free body diagram for the hanging mass.
Okay,
You got FG like that.
yeah.
You got FT like that. Accelerating that way. If I add FG and FT,
And that has to be the FU.
yeah.
Oh,
So FT
So
equals.
yeah, this is 5. That's 4.
FT
That's
plus?
1. Something like that.
Oh, why did you write it like
Now, in
that?
actuality, it's more like that.
Yeah.
FU is really small.
Okay. Okay, I understand. Why did you write it FT equals FT minus Okay, and then and then we found okay. It's like 14.7 seconds, and we knew that it fell. So that's the area, and you find that and find velocity. Yeah, and then find velocity. Okay. And so then yeah. So then we took that and we kicked it there. We're going to do the FT minus. Okay, so this is our tension.
There's a picture
And then this is all it works. What is it,
tension?
tension?
And they had like
Tension.
torque, and I don't know if you've seen that.
So then the torque.
Is they have all the 5 they just work right.
You're right. So this is our tension. So then it was this. So it's the force times what's the 1/2?
the radius, or this thing, this
Oh, times the radius. And then it's like.
And
Okay. So then you found the torque of. Is this the force on the. Yeah. So then that times that.
What did you guys have for tension? 4.89-ish?
And then you can find the circular acceleration by doing that. Okay. Then you divide it by the radius. And then
it was really confusing.
yeah, a lot easier now.
We just had to get through it.
Yeah, today's your first day. It takes a second. So we do that. FT minus FU is that via that. Then you find the FU, you find the FT, and then use the FT to find the torque of the tension. And then torque of the tension is the torque of balance. So it's inertia times that. Okay, so I kind of get it. My brain kind of hurts, but it's okay. Okay, you can do whatever you want to do. Really?
What?
Oh, mine's stuck. Don't look at what? Oh my god, you know. Where's the problem that's limit as it goes to 0? 0. Could have used what we call now.
Alright, so some of the business I got going on up here, we got a tension to be somewhere in the ballpark of 4.9. Like it basically the forces are the slightest bit away from being perfectly balanced. So there's 4.897 newtons.
Because he like plugged
The
in some stuff. You can't see
spindle over there.
Make sure you know how to do
The
that.
spindle radius is giving you how far away that force is being applied from the axis of rotation. So that's why I have 0.0239 here. Yeah, you can quiet down. I can stop shouting, and I'm going to be a happier boy. So, long story short, I get the unbalanced torque or the net torque on the apparatus to be 0.017 meter newtons. And then from my graph here, the motion of the thing, I get the linear acceleration to be 0.0060 meters per second squared. I divide that by the radius to get the angular acceleration of 0.253 radians per second squared. Because again, it's 0.0239 meters per radian, if you will. That's how the radius operates. I'm taking this and solving it out for the moment of inertia. If I take that unbalanced torque divided by that angular acceleration, I get that the moment of inertia for that apparatus is 0.462 kilogram meters squared. That apparatus consists of some thin aluminum bits, and then it's got these two big suckers. They're located 40 centimeters from the axis of rotation. Okay, there's two of them. So when I'm setting this up, when you have an object that can be thought of as just a mass, a point mass, some distance from the axis of rotation, like that's what this represents. The moment of inertia is just the mass times its distance from the axis squared, mr squared. That's the moment of inertia point mass there, IPM. Again, there's two of them. Okay, so I'm just saying 2m times 0.4 squared, because 0.4 is how far they are from the axis of rotation. So we solve it out for m, and what are you going to get there? You got 1.25, 1.35. They did it a slightly different way. Let's see what you folks get. 1.42-ish, okay? 1.39. So Tomas, you go ahead. So I've got this thing on here. Okay, this, like these balances only read up to 500 grams, and then you stick this on the end, now it reads up to 1.5 kilograms, okay? And we're expecting it to read 1.39-ish, right? So go ahead and put 390 on the triple beam, and then effectively it's 1.39 kilograms, right? Gotta get in the notch there, bro. There you go. All right. 1.399. That's what he's going for here. 1.390 now that he's sensed my sarcasm. All right. Dang it. What'd you do? All right. Figure out the actual mass of that thing there from us. It appears to be a little bit less massive than we thought. Don't lose that part. Kilogram part is legit. Try 200. Change it. 200. Now change it. Less. Oh, wait. Oh, you're close. Keep going. Oh. So that's effectively 1 kilogram and 200 grams. So 1.2 kilograms. So we're in the ballpark, but something else must be contributing to the moment of inertia here besides just these masses. Okay, they're not quite as massive as they would need to be to make the moment of inertia 0.162. Whatever might be responsible for the remainder, the difference in the moment of inertia. Use your words, Riley. The thing, says Riley, the thing over there, right? There's some stuff that was spinning. Do you sense that stuff could have the potential for injury if it were to be rotating? Okay. So here's what I propose to do. So we know these masses now. Thomas, they're how much? How much are these? 1.2? Okay, 1.2 kilograms. So let's figure out how much of the moment of inertia is attributable to these point masses. Okay? So if we take 2 times 1.2 kg times 0.4 meters squared, we get how much of the moment of inertia is due to the point masses. I get 0.384 kilogram meters squared. Okay? That's the moment of inertia due to the point masses. So that's what we calculated to be the total moment of inertia. I got to do a little math here. 0.462 kilogram meters squared minus 0.384 kilogram meter squared 0.6. Is that right? 0.078 kilogram meter squared. Fans of math? Okay. So that means the moment of inertia of the stuff is 0.078 kilogram meters squared. Okay? Stuff. So everything that you see over there still. The bits that we're spinning that aren't these two things. Okay? So if that truly is the moment of inertia for that stuff, here's what I need you to figure out. All right? If I hang a different amount, if I go with a hanging mass of could do 500 grams again. Sounds dangerous though. Let's go with a hanging mass of 100 grams and a delta Y of 80 meters, 0.8 meters, 0.80 meters, 80 centimeters. How much time will that take? Given that the moment of inertia of the stuff is 0.078 kilogram meters squared. Okay? So that's what I'd like you to ponder with your frienderinos. So kind of we're working the problem backwards. Now we're taking as fact that the moment of inertia of what's going to be rotating is 0.078. So if we have 100 grams falling 0.8 meters, how much time will that take? That's all connected up. Okay. Get at it. Yeah. No, the masses are not on there. It's just what's over there. So that's why I'm saying now we have a new, much lower moment of inertia. It's only 0.078.
But then aren't you going to put mass on it? Oh, no, it's the hanging mass is that one. Okay. I was confused.
You're okay. What up?
What?
Uh-oh. Uh-oh.
Okay.
Instead, I'm ordering mine from Australia. I talked to the
Australia?
How would you?
DTAC. Yeah, we've got
We
like
might do
built
the
in like
math.
electronics
No.
to like speed you
Hanging
up.
mass, 1 kilogram. I think
Yeah. So it sounds like,
we're not putting weights on it anymore.
yeah.
We have a different,
So we do need
Your brakes and
Yeah,
you can't stop.
oh, sorry.
Exactly. So then like, you have no wires on it. You just have to two shift your.
We can't really just do that.
So we're trying to find deltas.
Small equals zero.
I'm scared. Remember, like, yeah, I just gotta think about like how difficult is it to get my phone to like Bluetooth reliably to my speaker on
If you really wanted to use it, you can technically program
Give me wires. Give me wires. I want
Okay,
wires.
so we have
Don't like now.
new moment of inertia is 0.078.
I feel like
So basically,
Delta Y is 8.8.
just that spinning arm now, hanging mass.
Mhm.
And what we're doing is,
Was it 100?
0.07.
Oh.
so basically, it's just going through this backwards.
Alright, so way back in the day, we dealt with Atwood's machines and multiple body problems. And the thing that connected them was that their motions had to be identical because they are connected bodies. And that's what you have over here. So if you recall, kind of the key to that was establishing the FU over M relationship for everything. Because they have to have the same acceleration because they're connected by a string. Okay. That same thing is going to happen here, except you also have something that's rotating. So for it, unbalanced torque divided by moment of inertia gives you the angular acceleration. Angular acceleration can be related to linear acceleration through this sort of understanding, or this sort of understanding. Okay, so we have a way of getting back and forth between these two things. So you got to think about, okay, for the thing that's moving linearly, that's the hanging mass. How is its free body diagram going to look? You're going to have downward mg. You're going to have 0.1 times 9.8 newtons per kilogram. Yo. That pass looks like it was signed by someone named Leggy. Is that a nickname for somebody somewhere? That's an L. That's a cursive L. That is not a P. That is an L. Leggy. She's leggy from now on. All right. So, hey, this is the hanging mass. It's 100 grams. So you got FG downward, 0.1 times 9.81. Okay, this should be kilograms, newtons per kilogram, minus FT. That's how you would get the unbalanced force for this thing, right? And it's over 0.1 kilograms. Unbalanced torque over here. What's causing the unbalanced torque on the spindle? What's causing the spindle to want to rotate?
The torque.
It's caused by what? What's making that thing want to... What is interacting with the spindle trying to make it turn? There's a string tied to it, right? Okay. So FT, what is the position vector for that force relative to the axis? That's the other thing I didn't write. Well, did I write it up here? I wrote it up here. Spindle diameter, right? Spindle diameter is 0.0478. Spindle radius is 0.0239 meters. I'm unaware of any other torques acting in this situation. Now I got to divide it by the moment of inertia of the stuff. What is the moment of inertia of the stuff? That we got from up above, yeah? 0.078 kilogram meters squared. Ooh, so does this equal this? No. Why not? What do we got to do? Yeah, you got to translate, bro. It's this business. Okay? So either I can take this thing, this thing, and if I want to go up here and set them equal, I've got to take this thing and multiply by R. I've got to multiply by 0.0239 meters. Okay, and then I can solve for FT, and then I can go back into one of the equations and make a graph and stuff.
So that's done equals this. Because we're finding 2. So you can just solve it as 2. Yeah. Divided by 0.07. What are you doing? I'm solving it. Yeah, but like. Oh, I was multiplying these first. Multiplying and then dividing. Do you want that number? Okay. I got 0.0073207. No, 2 zeros. 0.007. 732 X.
Oh, wait.
Oh. No. Okay. And then do you want me to find this one? Yeah.
Wait.
Is that already over this? Yeah, that's already.
The unbalanced force on the 100 grams is going to be this gravitational force minus that.
9.81 minus FT.
This can
Oh,
come down
minus
to our
FT over
unbalanced
0.1.
force for the spindle, which is the tension times the radius for the spindle,
This
divided
is
by the moment of
and then
inertia.
you divide by this, then it's
To
just
get them to inflate,
right? Yeah. And then
I have
minus
to
FT
take
over
angular acceleration, which is what we solved for, times R. Now they are
or 10.
the same language.
You're solving for FT right here, right?
Yep.
This top
We're solving for FT.
What?
But this is like FU.
Yeah. So this equals this. 0.00732.
Balls.
Balls. And then, is that right? I don't know. Because this is 10 FT, and then this is that. It is 10 FT, right? Yeah. Yeah, good job. So 9.81 divided by
Suck.
10.00732. Oh, sorry. Yeah. 0.9803.
Ah, what was
So
it?
now we're still looking for time. So we're going to find the FU, right? And then do FU mass acceleration. So that's this.
These are.
So now our acceleration. So like we know what the yeah. So we need to find the acceleration.
Aight, what do I get for FT here? FT. Oh, I never solved for it. That's annoying. Le pube.
Oh, gotcha. Why is it over 0.1? That's the max. Okay.
So like when you solve like does it normally be 4 when you do it? Or is it just like
Negative number.
like if you just solve it like this, if you get like a continuous For after
What is that?
so
Oh, yeah. Okay, that's
back,
right then.
so you solve that, and you say f times 0 equals you realize the value of
Okay, now you get divided by 1.007. That's meters per second.
it is like, yeah.
But then also our slow. We don't know how much time it took,
It's not dynamic.
but we do know the distance. Right? The distance was 0.8.
Is the difference
This t squared equals divided by 2 equals this. Wait. What? 0.0072 find this times t. So 0.007 squared. Triangle equals 0.8. Yeah? Okay, so we're doing base times height. So base is t, and then this is the slope times t, right? Base height.
Oh, yeah.
So yeah, base times height divided by 2. So then divided by 0.07. Square root of that is 15.12 seconds. That seems pretty long.
Yeah.
The other one was what? Okay, then maybe we did it right. Oh my goodness. I'm proud of you.
double prime. F0 prime. That's like, when it's just like, bring it from the F.
15.12 seconds.
Like that's F2 is 0.
Now.
It's like, okay, well, we used 19. Well, maybe not. The numbers were so small.
Yeah.
Yeah, this is
So it's elevation. Oh, but you used 19.
Yeah, it's different.
Oops, that's wrong. What did I just do?
So he's lifting right now. The acceleration he got 0.01. How did you get 0.01?
Because ours was 0.9803, so like she rounded down.
Ours is just more precise.
What'd you get?
Wait.
I like yours better. I did something wrong.
We got 15.12. For our attention, we got 0.9803.
Ah.
We kept a lot of 6 figs.
I should have kept more sig figs.
I know, because that's super icky.
All right, let's see. 0.981 divided by 1.0000732 90803 981 minus 0.9803 divided by 0.1. You got 007 here? Okay. Yeah, I knew it wasn't right. Easy, bro.
Oh my goodness, really? Well, I think also you had just put 0.01 instead of 0.0. Oh no, that would have been 0.0.
Now we're getting like 15.
Yeah, 15.12.
Okay.
So we did it right?
Maybe. We haven't checked it yet.
Oh, I hope we did it right.
All right. So what I got going on up here is the dynamics version of this problem. Okay. And again, that's where I'm setting up Newton's second law statements for both things. F over m is linear acceleration. Unbalanced torque over I is angular acceleration. If I multiply angular acceleration by r, then they are equivalent. That's an important step in making these things translatable, if you will. And then I do some algebra, and I didn't keep enough digits initially. But when I go back in, I get a tension of 0.9803, which is significantly different than 0.980, given that the gravitational force is 0.981. So I find the difference between those two things divided by the mass. I get an acceleration of 0.007, and that gives me a time of about 15 seconds. Now I want to take a look at a completely different way of getting at this, which would be conservation of energy, and that's what those lads down there did the first time around. How is the potential for injury stored here initially in the system? Okay, so how, like, what is in the guise of what? What is going to change here that's going to relate to gravitational injury? Of the hanging mass, right? So if we think about our Lowell, there's some potential for injury stored in the gravitational interaction of the hanging mass. HM, spinny. Okay. And then in the end, that injury right before all the EG is transferred, you're going to have some EK rot, the spinny stuff. You're also going to have some EK tran, and that's the hanging mass. Okay. So I'm going to just go ahead and guess that more of it's in rotation than in the motion of the falling thing, because if you looked at that spinny thing, it looks dangerous. Okay, so EGA equals EK rot plus EK tran. I have no concept of where I am in the clock here. Do I need to be done, or where are we at? All right, so mg delta y is going to be 0.1, 9.81. Delta y we said is going to be 0.80. Okay, EK rod is going to be 1/2 of the EK we said is 0.0078. Is that right? E times omega squared plus 1/2 0.1 times v squared. Now here's the thing. The meters per second of this velocity have to match the tangential velocity at the rim of that spindle. So I'm going to go into this omega and recall that omega is v over r. So this is going to become this is going to become v squared. Hey, erase, dude, when I tell you to. V squared over r squared. And I know r. R is 0.0239. I have to remember to square that. If I do this, I can solve it out, and I can get the velocity. Okay, hey, that allows me to solve for v, and then I can go up into this thing and solve out from there, okay? But I don't think we have the time, so let's go check it out. 15 seconds-ish is what this is supposed to take. We already had 42.
Is that like another way to find it? The energy. I'm not good at the energy versions.
The long story short that I was trying to long story short you there is that the energy method can sometimes be a little bit of a simpler way of solving these problems. All right, timers at the ready. We'll get this show on the road here. All right, so that's 0.8 meters. Timers at the ready. 3, 2, 1, go. Everybody gets the floor. Now, when you're looking at this, what looks more potentially injurious? This whipping thing here, or this little mass of moving stuff? And I missed the button, so I was trying to stop the thing. What'd you get? I got a 15.2 here. I got a 1 person timing. All right, 15.2 seconds, which is close enough to government work for 15.1. Okay. If we solve out this velocity, 0.5 times 0.0078 divided by 0.0239 squared plus 0.05. And then the other side is 0.1 times 9.81 plus 0.8 divided by.
To make it.
Just the times two has to, because think about it, it's
Because it's supposed to be b squared, so it's the b you're using to English, the lead of bonds, and then it's b squared.
So I'm not sure I'm trusting this number. We'll find out in a second. I get 0.114 meters per second. And if I do a little 1/2 base times height, 0.8 times 2 divided by 0.114. Yeah, I get like 14 seconds. Something kind of in the ballpark of, okay? So, hey, long story long. All this work, if I go about it using Newton's second law of dynamics, all that work, if I go about doing it with energy. Energy is often very clean, relatively speaking. Bro?
Equals 1/2 m, and then is that angular
This is
velocity?
1/2 I, and this is omega squared, and I'm substituting in V over R for omega, so that's why I have B squared over
That's
R.
the equation for
That's what I did do. I didn't take the square root of what I had there.
what?
I bet.
What's the equation for rotational energy?
0.8 times 0.2. No. 0.114. If I take the square root of 0.114, I get okay. 0.8 times 2 divided by 0.337. That's not what I was looking for.
What's rotational energy?
E.
Yeah.
Yep. I think I forgot to take a square rootage somewhere here, though.
Like
I can take care of it.
0.06 for my
Yeah, I have it open. So take the test.
Of this one, too.
I don't know about that.
Good luck.
That's what I had on the initial one, was 0.006.
I had 0.06. So I got like 5 seconds.
You did it wrong, then.
Yeah.
Feel like my helpful feedback? All right, gosh darn it, what did I do here? All right, 0.1 times 9.81 times 0.8
Now I can't find my notes on my calculator.
divided by 0.5 times 0.0078
Good luck.
Thank you.
divided by 0.0239 squared. Plus 0.05. Dude, what'd I do? $338 is too big. Two. That's massively wrong. Aye.